Take another look here at chapter 5. Our main goal in this chapter is going to be integration. Now, along with differentiation, integration and differentiation are the two big ideas in calculus, and we're pretty good with the first one already with differentiation. So we're ready to introduce that second big idea of integration. And just to summarize real quick, what do we know about derivatives from calculus so far? We know how to differentiate, so compute the derivative of nearly all types of functions using the product rule, the chain rule, all the rules that we know. And we know that differentiation can be thought of graphically, looking at little bitty changes in the function to find the exact slope or the instantaneous slope, the slope of the tangent line, as opposed to a secant line. And we also know that differentiation can be thought of as an algebraic process, a mathematical operator. And so just like many operators, it's going to have an inverse, like addition, subtraction, exponentials, logarithms. They all have inverse operators. And so that's what we're going to be looking at to start this section right here. We're going to do some backwards differentiation or anti-differentiation. And so the first thing that we want to define is what the antiderivative of a function is. So we have some notation for derivatives. In derivatives, we know that if we have f, little f, of x, we know that its derivative is f prime of x, but we don't have a name for what it might have come from. It's antiderivative. So its antiderivative might be called capital F of x, is the notation that we use right here. So a function capital F is an antiderivative of little f, provided that capital F prime is equal to little f. Okay, so capital F's derivative is little f. So those are our notations. If we start with some central function f, its derivative is f prime, its antiderivative is going to be capital F. Okay, there are other notations, of course. If you start with an f prime function, well then you already need to only go backwards to f. So if you start with the g prime function, its antiderivative is g, but if I start with something that's just called f or just called g, I would go to capital F or capital G for the antiderivative. That's our first set of notations. We're going to get a little better at notation as we continue. So, in our first example, in order to do antiderivatives, we need to retrain our brains to think backwards. So let's say if we know that f prime of x equals 2, what would f have to look like? And so the derivative is, remember, slope, right? So the derivative is giving us the equation for slope. It's the equation for slope at any point. Now in this case, it is a constant slope, and so I'm going to be able to draw that. So I need a function that has constant slope where the slope is 2. So I could draw something like this. This is a linear function. I'm doing a rough sketch without a ruler here, so hopefully I managed to have a slope of 2 on that. This is a line that has slope 2. But so is this. This is another line that has slope 2. So those both satisfy the original condition that the derivative is going to be 2, f prime of x equals 2. How do I know which one of these is f of x? And the short answer is that we don't. F of x is going to look like one of these two things. I mean, it doesn't have to be just stopping at 2. I think I messed up the slope on that one. So a little more careful with the rise and run there, but that's okay. So it's anything that's a slope of 2. So I don't know. And so getting into that, I know that there's a pattern between them. And so when we talk about the antiderivative, we have to talk about them in terms of a family of antiderivatives. So there isn't going to be just one, because there are going to be many things that have the same slope or have the same derivative, many parallel functions. So capital F is going to be any derivative, antiderivative, I meant to say, of little f, and all antiderivatives of little f will have the form capital F plus c. So I'm going to need to make sure that when I take the antiderivative of something, I keep in mind that there might have been c, an arbitrary constant at the end of it that I cannot tell. Okay, so back up on this idea. If I had some functions, f of x equals 2x plus c being the antiderivative function, because I know its derivative is going to be 2 plus, it doesn't matter what c is, the derivative is going to be 0. I just can't be guaranteed to know what c is. There's no way to know what c is, so we leave it as a variable. Okay. Now, it's easiest for us to visualize this in the linear case because we're all very experienced at drawing linear curves, but this is going to be true of any curve. So I might have something where the antiderivative function, again, isn't a line, but you can see that it might have a whole family of antiderivatives with different c functions, with different c constants. This is just another graph of that family. Okay, this is, again, one in the linear case and one in a non-linear case, looking at a family of antiderivative graphs. Okay. So with that taste in mind, we got a couple functions here. We want to find out what their antiderivatives would look like. Okay, so I need to know what function would give me a derivative that is 2x. And so we're going to build up a procedure for this, but right now it's some memory at the moment. I don't have a procedure yet, but I know that if I take x squared's derivative, I get 2x. So that helps me build the capital F of x function. It's going to be x squared, but I don't know if it was x squared plus 1 or x squared minus 3, so I have to put that plus c on there for the family of antiderivatives. X squared plus any constant number will have a derivative of 2x, and so that is my answer for the antiderivative. Okay, so we're undoing a little bit of some of the differentiation rules here to try to find an antiderivative. Okay, so they're going to get a little more interesting here. Now, in the next one, this is a power function, and for derivatives, remember, we would be taking the power down and then reducing the power by 1. So I have to do the opposite of that to do an antiderivative. We have to increase the power by 1 and then divide by the new power. That makes sense. We're going to build this rule, and it is more formally stated on the next page. But what I'm trying to say is I'm trying to remember what the rules are for differentiation. How do I differentiate something that is in that form, and how do I undo that? So the capital H of x function here would be, if I take negative 7 plus 1, that's going to give me x to the negative 6th power. And if I divide by negative 6, the negative 6's cancel off. So back to the original was negative 6 x to the negative 7. That is the derivative of x to the negative 6 plus some constant. So negative 6 down, 1 off the power, gets me back to that. So if I take the derivative of capital H, I get lowercase h. So this is the antiderivative. Okay, so a little bit of thought behind how I get that, and then we're going to build some rules around that next. Okay, in part C, we have a little r of x function, so I want to find its antiderivative. This is a constant, and so I know that I get a constant if I take the derivative of a constant times x. So this antiderivative must be pi x plus c, right? Okay, because the derivative of pi x is pi times 1, and that's what I've got right here. Okay, and then again, little g of t models what h did, and so if the power used to be 11, when I brought it down, my 11 would have come down, I would have reduced it by 1 to 10. And so capital G of t is, I almost wrote an x, but it's t to the 11th plus c. Its derivative, again, 11, t to the 10th. So I'm back to little g by doing the derivative, so I know I have the correct antiderivative. All right, that gives us a little taste, a basic understanding, hopefully, of the process of antidifferentiation. And now we're going to really need some notation to use with it. Okay, so first of all, the d dx is the notation for find the derivative of the function. And so we already have that notation. What we need is some notation for find the antiderivative of the function. Okay, we use this, it's called the integral symbol. It's an elongated S because integrals are tied with sums. So the S really does stand for the sum, and we'll talk more about sums as we get into the rest of chapter 5. We're getting into that soon. So we have that strange new symbol. It's the integral symbol. It's a elongated S with tiny little curls on it. It's called an integral. It always appears in conjunction with the integrand. So that's the function. So I'll start labeling. We have our integral. F of x right there is our integrand. And the differential. Okay, and then, of course, we called the symbol itself the integral. So we have the integral, the integrand, and the differential. So the differential, which in this case was dx, is also important. And actually, we kind of think about the integral and the dx as being sort of parts of parentheses. So they go together like that. So I can't have an integral without a differential. Okay, so I need to think about these as being two sides of closing parentheses. They don't look like the same thing, but I need to have one at the beginning and one at the end. So I do need both of those as a pair to close, or to open and close an integral. Okay. Taken together, this whole thing is called the indefinite integral. So just what I mentioned, that it's called the indefinite integral because we will talk about definite integrals later. I'm not going to get into that right now. When we get there, we'll be ready for it. But right now we have an indefinite integral. Okay, so it is equivalent to say that the indefinite integral of f is the antiderivative of f. So there are two different ways of saying this. So the indefinite integral, integral of f is the antiderivative of f. Another way to say that, which might have just used less symbols, would be to say that the integral of little f of x dx is equal to capital F of x plus c. So our indefinite integral is the antiderivative in the general form. Okay, so I'm going to use this new notation to state the antiderivative from example 2a above. Okay, so we would say that instead of just giving me little f as the function 2x, we would write, we want to find the integral of 2x dx, and our conclusion is that its antiderivative is x squared plus c. So this is how I would write it in integral notation instead of just antiderivative notation. This notation has lots of advantages in the fact that I don't have to name this function and rename that function with a different name. I can just do the process. Okay, so we're going to be using the integral notation a lot as we practice our integrals.